To answer the question, we have to introduce sampling theory. What we want to do is, can we recover the original signal from the sampled signal without any information loss? Instead of doing this in the time domain, an alternative way is we convert both signals into Fourier representation, and then we study the relationship between these two spectra. And the understanding of the relationship between them will help us understand in what situation we can recover the original signal from the sample signal without any information loss. Before we introduce the sampling theory, I want to refresh our memory of this signal. It is impulse train, and here is the graphic representation. Then what is the Fourier transform for that impulse train? Well, it is another impulse train in the frequency domain. And here is the graphic representation. And the interval in the time domain and the interval in the frequency domain satisfy this equation. Now, let's try to look at this signal. Sampling signal is defined as the multiplication of the original signal and the impulse train. Based on the convolution in the frequency domain, the spectrum of this signal is equal to the convolution of the spectrum of x of t and the spectrum of impulse train, subject to this scaling factor. And we can simplify it into this equation. This actually is the periodization of the original signal's spectrum. But this equation can be represented using a different format. So we can plug in the definition of the impulse train to get this summation. Then what is the Fourier transform for this summation? Because x of k times capital T has nothing related to t here, so the Fourier transform for the multiplication, the Fourier transform for the summation is equal to the linear weighted combination of the Fourier transform for the dot train. So this will be the Fourier transform. We can rewrite it in a different format by substitute omega times capital T by capital omega. Then this part will be equal to this summation. Pay attention to k. It is an integer number, so effectively this signal is a discrete time signal. And look closely at this equation. It is actually a definition for the discrete time Fourier transform of x of k. So the conclusion here is the Fourier transform of the sampled signal is equal to the periodization of the original signal x of t. So here is the sampling theory. If we know this relationship, or the signal is sampled in the continuous time domain, then the spectrum of the sampled signal actually is the periodization of the spectrum of the original signal. There's some relationship we need to pay attention to make use of it. First of all, the independent variable in these two parts are not the same, and there is the relationship between the capital omega and the small omega. Also, the interval of the sampling in the time domain also related to the sampling angular frequency in the frequency domain. And here is, one more time, the correspondence between the time domain and the frequency domain. Sampling in the time domain corresponds to periodization in the frequency domain. So that correspondence tells us, review that the essential of the sampling theory. Let's use an example to explain what is spectrum periodization. So we have a continuous time signal x of t, and this is the spectrum. What if we sample the signal using an interval t equal to 0.01? According to the sampling theory, the spectrum of the sample signal is actually the periodization of the original signal spectrum. The omega sub sam is defined by this equation, so we can calculate it. It's equal to 200 pi rad per second. So if we plot it, for example, if we let n equal to 0, then this term is the original spectrum in here. And if n equal to positive 1, then the spectrum has to shift towards your right by omega sam. So that will form this plot. And if n equal to positive 1, you have to shift this spectrum towards your left by the unit of omega sam. And when n equal to 2, you have to shift it by 2 units of omega sam, or the other way around. You can do this so on and so forth, since n change from the negative infinite to the positive infinity. So this is the periodization of the original signal's spectrum. And they have different independent variables, and the relationship is defined by these equations. So you can plot it using the omega, small omega, as the independent variable, or by this definition, the same plot, same spectrum can be represented using a different independent variable. This will be the graphic representation using capital omega as the independent variable. Now we have the sampling theory. Sampling in the time domain corresponds to the periodization in the frequency domain. Let's take a look at this band-limited signal. And the maximum frequency, or the angular frequency, is equal to omega sub m. Any frequency components greater than this value will be equal to 0, so we define it as a band-limited signal. What if we sample that signal with a angular sampling frequency omega sub sam? In case the sampling frequency, angular frequency, is greater than 2 times the maximum frequency of the original signal, this will be the spectrum of the sample signal, and there's no overlap yet. In case the sampling frequency is twice the maximum frequency, although there is a contact in here, but the shape of the individual waveform still intact. However, if you push over the limits, then the individual shape of the waveform of the original spectrum going to be lost. So that will be problematic because you won't be able to get the original spectrum out. In other words, you won't be able to recover the original signal x of t using this sampled signal. Since there's some overlap in here that significantly change the shape of the spectrum, we won't be able to identify the individual waveform that's similar to the original one. So we won't be able to recover the original signal. And this phenomena is called aliasing. So for band-limited signals, if the highest angular frequency for the band-limited signal is omega sub m, in case that the sampling angular frequency is greater than or equal to twice the omega m, or the sampling frequency is greater than 2 times the maximum frequency, or in other words, if the sampling interval in the time domain is less than or equal to 1/2 times the maximum frequency, then there's no information loss, and we can recover the original signal xt from the discrete time signals spectrum. But this is the sufficient condition. That means if you satisfy this condition, you're going to recover the original signal without any loss. But even if in some situation we violate these criteria, we may also have a chance to recover the original signal without any loss. And this specific frequency, 2 times maximum frequency, is the minimum sampling frequency. It is also known as Nyquist rate. That term is named after this person who is the first proposed that for band-limited signal, the sampling rate must be at least twice the highest frequency for us to recover the original signal. Here is one situation that even if we do not follow Nyquist frequency, do not follow that criteria, we also have a chance to recover the signal without any information loss. This is called high-frequency narrow-band signal. The highest frequency is pretty high, but the band of the signal is very narrow. So for this type of signal, we may have a chance to sample it with a pretty low sampling frequency, but still have the ability to recover it without any information loss. Here is one example. For this signal, the highest frequency is equal to 56 kilohertz and the bandwidth is 8 kilohertz. What if we sample the signal less than twice the maximum frequency? For example, if we sample it at 16 kilohertz, so we will have to periodize the original signal spectrum. That's for that part, periodization, and for this part, periodization as well. And you can see that in this periodized spectrum, there's no overlap. We can still identify the individual spectrum for the original signal. So we have a chance to recover the original signal from the sample signal, even if the sampling rate is significantly smaller than the Nyquist rate. This is another case. The maximum frequency is equal to 28 kilohertz. And we can use the bandwidth as the sampling frequency to see whether or not we can recover the original signal. So this is for that part, and this is for this part. So periodization of the original signal will yield overlapped spectrum, but the shape of the overlapped spectrum does not change the shape of the original spectrum. So in this case, although there's overlap in here, we are able to recover the original signal. So these are two situations that even if we violate the Nyquist criterion, we still can recover the original signal without any information loss, or there's no aliasing in here. But not every single signal can be this lucky. The previous examples show us that the Nyquist frequency actually is the sufficient condition. In case the signal, they are high frequency narrowband signals, we may have a chance to recover the original signal without any information loss using a sampling frequency significantly smaller than the Nyquist frequency. Now let's consider two questions. One is, can we always recover a high frequency narrowband signal if we sampled it at a sampling rate equal to twice of the bandwidth? The second question is, if we can recover it using the sampling frequency equal to twice the bandwidth, can we recover it using any sampling frequency that is greater than twice the bandwidth? For the first situation, let's take this signal as the example. Now we have the maximum frequency equal to 26 kilohertz, and the bandwidth is 8 kilohertz. We can use the sampling rate equal to twice the bandwidth, which is 16 kilohertz. And here is how we periodize the signal. And there is some overlap in here. And this will significantly distort the original signal. So we won't be able to recover the original signal anymore. So the first question is no. For the second question, if we can recover the signal using the sampling frequency equal to twice the bandwidth, what if we use an even greater sampling frequency to do the sampling? Now let's set it equal to 18 kilohertz. And this is the periodized spectrum. And we see one more time that there's some overlap, and this overlap actually will change the shape of the spectrum. So we won't have the chance to recover the original signal. So the answer for the second situation is also no. Here is a comparison for distorted spectrum and spectrum without distortion. So the sampling rate is 8 kilohertz, and here the sampling rate is 16 kilohertz. Although the sampling rate is higher in that situation, there is aliasing happens in here. So whether or not the aliasing is happening depends not only the bandwidth, but also the shape of the spectrum. In this example, we know that for a real band-limited signal x of t, if the maximum frequency is given f sub m, then what are the minimum sampling frequencies for these 5 different signals? Because compression in time domain corresponds extension in the Fourier domain. So for the first situation, we can get the maximum frequency for this signal is twice the maximum frequency of the original signal, so that the minimum sampling frequency gotta be twice the maximum frequency for that signal. So the minimum sampling frequency actually is 4 times the f sub m for the first signal. For the second one, the original signal convolutes with the compressed signal. Due to the convolution in the time domain, we know that in the spectral domain, in the frequency domain, the spectrum are in multiplication, so that the maximum frequency is determined by the original signal. So the minimum frequency for sampling actually is equal to twice the f sub m. For the third one, this corresponds to compression in the frequency domain, and this is the extension in the Fourier domain. So the maximum frequency actually is determined by this compressed signal. So the maximum frequency actually is f sub m divided by 3. So the minimum sampling frequency actually is twice that frequency. For the fourth signal, multiplication in the time domain corresponds to convolution in the frequency domain. The maximum frequency is equal to fm plus twice fm. So it's 3f sub m. That is the minimum sampling frequency. And for the last one, linearity property tells us that the maximum frequency actually is equal to twice the fm. So the sampling frequency must greater than 4 times f sub m.